Alright, now we're talking about saturated liquid vapor mixture. So that's the next topic for chapter 3. So then continue our chapter 3 discussion. So this is now it's a saturated liquid and vapor mixture. Okay, so when we talk about saturated liquid and vapor mixture, we're basically, if you remember our discussion about the saturation curve, which, for example, if we had here on the vertical axis, we said P, or this could also be temperature, and on the horizontal, let's just suppose now it's a specific volume, so that's meters cubed per kilogram. What we're going to have is we're going to have a saturation curve, if you remember. It looks something like this. And everything on the left hand side of the curve, when we up into the point here that we call P critical, everything left of P critical on the curve itself is called saturated liquid. And everything to the right of P critical on the curve itself, it's saturated vapor. So in here lies a mixture that we don't really, it just depends where we lie inside this curve, that where we have what kind of mixture we have. Now for defining mixture, we use something called equality, and we call that X. So it's just a number. What it really is, X is a ratio signifying how much mass of vapor for a given total mass. So if we look at a point somewhere in here, and we look at this point, and roughly it's in the middle between saturated liquid and saturated vapor. At that point, we want to know what is the mass of the vapor at this point on the graph divided by the total mass, where we define mass, the total mass. So the total mass is equal to, it's the mass of the liquid. There's only two states that we're looking at, two conditions here. That's mass of the liquid plus mass of the vapor. So it's either liquid or it's vapor. And the total at that point is the total of the mass of the liquid plus the mass of the vapor. And you remember from the lecture, we say mass of the liquid, we give it a subscript of F, and mass of the vapor we give a subscript of G. So we're talking m sub F plus m sub G is mass of the liquid plus mass of the vapor. And the ratio of the mass of the vapor to the mass total is X. Now, what I tell students is the reason this was created this way, not mass of the liquid over mass total, is that in the early days of thermodynamics, when the Industrial Revolution was taking hold and we were using fossil fuels to power things like steam engines, on the steam engine, you wanted to find out how much vapor you had over the total quantity. For example, if you had a volume of some kind of saturated mixture, we wanted to know how much the vapor mass of that was per the total mass, and the higher the number, the better, right? The more vapor, the more power potential we had in that quantity of liquid. So that's why it's skewed towards mass of the vapor over mass total. So the higher the percentage, the better from that standpoint, from a steam engine power standpoint. And so again, if we look at a tank, a saturated tank, what I mean by saturated tank, just say there's saturated water in here, there's going to be a certain amount of saturated liquid. Let me just have a little triangle here signifying there's liquid in here. And so we can just say this is the mass of the saturated liquid. And over here is this gas here is basically the mass of the saturated vapor, m sub g. And so that's what we meant. And so this, equivalently, we just say that this is equal to, instead of saying it's a certain, let's say, so there's just a certain volume associated with this. There is again, if I was to draw the line here, we know that there is a specific volume of the vapor here, and there's a specific volume of the liquid. And I'm going backwards here, I apologize about this. Equivalently, instead of saying, well, we have a tank that has a certain portion of it is the volume of the liquid and volume. Sorry about this horrible drawing here. We can say equivalently, this is just some average. Some average saturated mixture. All right. And so that's, we're trying to identify what is the average here. So if I go down here and say, well, we don't typically say V sub average. We just call it a V, just V, and we eliminate the, we don't even use the subscript here. But right now, just to kind of tell you what we're trying to seek, we're trying to find what's the specific volume of a mixture given what quality this is. Okay, so let's go ahead and continue this discussion. Create a new page here. Okay. All right. So let's suppose that if we're talking with a total volume, from a total volume standpoint, sorry, let's go ahead, pick a color here. So we're talking about the total volume of a tank, call it V with a little line going through it, is equal to the total volume of the liquid plus the total volume of the vapor. Okay. And now, if you remember from our discussion in class, total volume is equal to mass times the specific volume, which is called that V sub little v with no subscript, and this is equal to the total mass times V average. And then this, the total mass, is broken into two components. There's the liquid, so it'd be the mass of the liquid times the specific volume of the liquid, saturated liquid, plus mass of the vapor times the specific volume of the vapor. That would represent the total mass times the specific volume. And if we were to go ahead and say that, therefore, if we want the mass of the liquid, we get the total mass, and from it we subtract, so this is a T, from it we subtract the volume of the vapor. And therefore, going back to the mass total times the specific volume of the mixture, we'll say that MT V sub average is equal to the mass of the liquid, which is up here, mt minus mg, mt minus mg quantity. So that's this represents the mass of the saturated liquid times V sub F, the specific volume of the saturated liquid, plus mass of the saturated vapor times specific volume of the saturated, sorry, that should be a G right there, saturated vapor. And if we divide by MT, thereby we find what we divide both sides by MT, we have now the specific volume of the mixture, which we call V sub average, and that is equal to 1 minus X times V, V sub F plus X V sub G. Now we remember that up here I'm going to go ahead and say, remember what X is equal to. It's equal to the mass of the vapor divided by the mass total. So that's where we get X here. When we divide mass total divided by mass total is just 1 minus mass of the vapor divided by mass total, that's X, and so forth right here. M, this is mass of the vapor, and divided by mass total is equal to X. So if we go ahead further, if we multiply through the 1 minus X times V sub F, we get that this is equal to V sub F minus X V sub F plus X V sub G. All right, so this is a minus here. And this, in turn, if we look at, now we can say, well, we have, let's collect our x's. So we have, here we have x times v sub g minus x times v sub f, and then we have v sub f here by itself. So if we go ahead and gather like terms, we're going to have that v sub f plus x times quantity v sub g minus v sub f. And what is that equal to? Well, we're going to do a definition up here. Let's say that v sub g minus v sub f, it's the difference between the specific volume of the vapor and the specific volume of the liquid. We're just going to give this a different term here. We're going to call it v sub fg. It's a term that we're going to use a lot. This fg represents anything, any property subscript g minus any property subscript f. So this one is specific volume of the vapor minus specific volume of the liquid is equal to the specific volume Fg. It just signifies the difference. And so therefore this is equal to V sub F plus X V sub Fg. All right, and this again is equal to our average specific volume of the mixture. All right, and this we use to represent all different properties. So for example, if we were talking about internal energy of a mixture, we would say the internal energy at a point inside the saturation curve is equal to the internal energy of the liquid plus X times the internal energy F sub G, which is basically the internal energy at the vapor minus the internal energy of the liquid. Okay, this is a U. All right, and also for any other property, let's talk about enthalpy. The enthalpy at that point inside the saturated curve is equal to the enthalpy of the liquid plus X times the enthalpy of the Fg, which is the enthalpy of the vapor minus the enthalpy of the liquid. Again, here we would say, okay, U sub G minus U sub F is equal to U sub Fg and then H sub G minus H sub F is equal to H sub FG. So in general, this is how we determine what a property is, and inside the saturation curve, anywhere inside the saturation curve. If we know, and we know that these properties, the saturation, the property at the saturated liquid and the property of the saturated vapor are table values, and we go to our table and pull those out. And all we need to have is, and as a matter of fact, the tables will and oftentimes have H sub Fg already in the table, although we can calculate it, right? It's simple enough to just get the enthalpy of the vapor, of the saturated vapor minus the enthalpy of the saturated liquid. That is the enthalpy of the mixture. Or in this case, this is called the enthalpy of the, this is an aside, but this is also the evaporation enthalpy, which basically when you get this term, when you subtract the enthalpy of the vapor minus the enthalpy of the liquid, you're actually getting the latent heat of evaporation. So this is how we determine properties. And at the very root of this is basically, at the beginning, we're basically trying to determine what's the specific volume of a mixture, and that's how you do it. But this, now I'm telling you in general, for any property, we would need to know the quality in order to determine what the property is at that specific point. Okay. All right, let's talk about some examples. Go ahead and bear with me. Okay. Create a new background. All right, so let's look first at example in the book. Example 3-4 in your textbook. So if we're going to go ahead and look at example 3-4, we see it says the pressure and volume of a saturated mixture. So we talk about a rigid tank. All right, so example 3-4 tells us that we have a rigid tank contains 10 kilograms of water. So inside here there's water, and the temperature of the water is 90 degrees C. And what else do we know? So it contains 10 kilograms of water, 90 degrees C. We know that 8 kilograms of the water is in liquid form and the rest is in vapor form. Okay, so I'm going to go ahead and overlap here and say that 8 kilograms of the water, just bear me while I draw this here like this. So there's a liquid line in here, and in here it says that there's 8 kilograms of the 10 kilograms, 8 kilograms is liquid water. And therefore there's, and I'll go back to a red, maybe 2 kilograms. The remainder, there's 10 kilograms, so 8 kilograms of it is liquid water, and 2 kilograms is equal to, let's say what this is. This is the mass of the vapor, and this is here, this is the mass of the fluid, or the liquid, the saturated liquid. So this tank here tells us that we're in a saturation state. We're saying part of it is saturated, it's a mixture, part of it is saturated vapor and part of it is saturated liquid. So it says we need to determine the pressure of the tank and the volume of the tank. So find the pressure of the tank and find the volume of the tank. All right, so pressure of the tank, because we know this is a saturated mixture. I was going to say this is a saturation mixture. Therefore, we go to table and we're given temperature. So we're given temperature. We need two properties in order to define the state of any given of a pure substance at any given situation. We need to have two properties. Well, one property is the temperature. Now, mass isn't a property. So we need an intensive property, which means it's independent of mass. So we don't have anything but temperature. Well, we do actually have one more thing. We have the fact that it's a saturated mixture. So this already, the fact that it's 90 degrees and it's a saturated mixture, we can find all the properties associated with the water inside this tank. So we have our two. We're given our two properties are. So therefore, we go to the back of the book. We go to table A4. So this is in the appendix. That's what the A is for. And if we go to the table A4, then we readily can get P, because the pressure of the tank is basically the saturation pressure. Remember, when we're in a saturation state, there is a unique pressure and a unique temperature. In other words, you give me the fact that we're in a saturation mixture, and then all I need is the temperature, and I can give you pressure, because this is equal inside that table. This is equal to pressure. This is the saturation pressure at 90 degrees Celsius. So that's a table lookup. So if we look up 90 degrees Celsius and we find that temperature or that pressure to be 70.183 kPa, kilopascal. So that's a table A4 lookup. And now to find the volume, we're going to need the specific volume of the liquid, and this is at 90 degrees C, or at 70.183 kPa. But the specific volume is equal to, this is a table lookup as well, is equal to 0.01036 meters cubed per kilogram. And we're also going to need the specific volume of the vapor at 90 degrees C. And this is equal to 2.3593, another table lookup, meters cubed per kilogram. And now we use these in context of the total volume. So we know that the total volume is equal to the mass of the liquid, saturated liquid, times the specific volume of the saturated liquid, plus the mass of the vapor times the specific volume of the vapor. And these we have already looked up. V sub F and V sub G we just wrote down. Those are table lookups. So luckily for us, we have the mass of the liquid and the mass of the vapor. It's been given. We know the mass of the liquid was 8 kilograms, and the mass of the vapor was 10 kilograms minus 8 kilograms, which is 2 kilograms. And now to get the total volume, we just go ahead and plug everything into the equations. To this equation is equal to, again, mass of the liquid is equal to 8 kilograms times V sub F, 0.0011038, plus mass of the vapor, which is 2 kilograms, times 2.3593 meters cubed per kilogram. So this gives us everything in terms, so it's when we multiply by the mass, it'll now give us a total volume, because we basically cancel out the kilograms at the bottom here. And we got now a total volume of 4.73. So this calculates out to 4.73 meters cubed. And that is the total volume of this tank. And so now we found the pressure of the tank and the total volume of the tank. Okay, so that was one example. Now we could have done this problem. We didn't use our quality. We could have done it another way. We could have basically said, I ran out of room here, so I need to start another page. Okay, we could have said that, well, the other way to do it is the same component. What's the equality? Well, the quality is mass of the vapor divided by mass total, which we knew the mass of the vapor was 2 kilograms, and we knew the total volume is 10 kilograms. Therefore, we have a quality equal to 0.2. So x is equal to 0.2. And from our previous discussion, we talked about what the specific volume of the mixture is inside the saturation curve. We're just going to call that V now, just V with no subscript. And we know that that is equal to V sub F plus X, the quality, times V sub G. And then we know that we calculate where we found through a table lookup. So I'm going to say through a table lookup, we know what V sub F and V sub G is. Actually, this is not V sub, this is V sub FG. Sorry about that. And now, and we can calculate what V sub FG is because it's a subtraction. So now we say, well, we know V sub F was equal to 1038. Let me see. Yeah, no, sorry, 1036. And we know plus the quality, which is 0.2, times now V sub Fg. Well, that's V sub G minus V sub F, which is equal to 2.3593 minus 0.001036. All right, and when you do this calculation, we're going to find out that the specific volume of that mixture comes out to be equal to 0.473 meters cubed per kilogram. And now to get the total volume, we multiply by the mass, the total mass, times V, which we know the total mass of the tank was 10 kilograms. And then we multiply that by 0.473 meters cubed per kilogram. And so we end up getting the same answer, which is 4.73 meters cubed is our total volume. So that was the other way of doing it, using quality of the vapor. Okay, now let's go ahead and start a new page here. Now we're going to do example, we're going to end off with example 3.5. In example 3.5, let's read it from the book. It tells us that, so we have properties of the saturated liquid vapor mixture. An 8-liter vessel contains 4 kilograms of refrigerant 134A at a pressure of 160 kilopascal. Determine A, the temperature, B, the quality, and C, the enthalpy of the refrigerant, and D, the volume occupied by the vapor space. Okay, so we're going to go ahead and draw what this looks like. So we have a tank. All right, that should be a solid closed off tank. In here is a refrigerant that's widely used for air conditioners and refrigerators. It's called R134A. So this is no longer water. This is another material. We know that there's R134A here in some kind of a mixture, and we know that the pressure here is equal to 160 K MPa. So that's 160 kilopascal. Sorry, I ran out of room here. And the mass, the total mass, is equal to 4 kilograms. But we know in here there is some kind of there's some liquidus in here. So part of this is liquid, and part of it is vapor. Now let's assume that this is it's solid. We can't see through the cylinder, so we don't know. We couldn't measure what this line was. So we need to be able to determine. At one point, we need to find the volume occupied by the vapor space. So we have all the properties we need. We need two independent properties, two independent intensive properties. So mass is not considered a property, an intensive properties. So our two properties, well, we have pressure, which is equal to 160 kilopascal, and we have the fact that it's a saturated mixture. So therefore now we can just use table to get all the properties associated with this substance. We're going to use a table in the appendix. This time we're going to use, previously we used table A4, now we're going to use table A5. And the reason we're using A5 is this is called the pressure table. The previous one was the temperature, A4 was the temperature table, because it's the first column on the table is temperature. For this one, when you're given a pressure, we use the pressure table, where the first column in the table is pressure. And it gives us nice round number pressure values. This is 160 kilopascal, so it's guaranteed to be there on the first column. So we use that. And all right, so the first thing we need to, so again, we need to find several things here. The first thing is we're going to need to find the temperature. Right, so that is readily obtained by going to the table A5. I'm sorry, did I say A5? I'm very sorry. This is no longer water, so we're not using water. We're doing saturated R134A, so this becomes table A13. So the pressure, I had given you the pressure table for water, but this is R134A, which the pressure table is A13. And so when we go to A13 and we need to find the temperature, we're finding the saturation temperature. It's the temperature associated with the pressure that we were given. That's 160 kilopascal. So we're finding the temperature associated with 160 kilopascal. We go down the column. When we run into 160 kilopascal, we go horizontally across to the next column over is the temperature. We find that temperature to be minus 15.60 degrees Celsius. Okay, so now we found our temperature, and we're going to need, in order, eventually we have to find the volume occupied. We need to find the quality. So I'm just going to say these are the things we need to find. T, we need to find the quality. We need to find the volume occupied by the vapor, phase. So I'm just going to say it like this, the total volume occupied by the vapor, I would say G. And we need to find the enthalpy of the refrigerant. So that's basically what the average enthalpy is of this refrigerant at this state. So we found the temperature. So we can check that one off our list right there. Now we need to find the quality. So in order to find the quality, we need to find our specific volumes of the liquid and the vapor. So those are table lookups. So V sub F for this 160 kilopascal table lookup, this is table A13, we find that V sub F is equal to 0.007435 meters cubed per kilogram. And now we have that V sub G is equal to 0.12 0.35, and that's meter cubed per kilogram. Okay, so now we can determine what the quality is. Now quality, we know from our equation, do you remember our specific volume equation for the specific volume of the tank? We know that this is V is equal to V sub F plus X V sub Fg, where V sub Fg is basically V sub G minus V sub F. Therefore, if we solve for X, we have that the specific volume of the tank minus V sub F divided by V sub Fg. And so we know that the so this was actually given 80 liters was the total volume. And so therefore, if we're given the total volume is equal to 80 liters, then we know that the specific volume of this tank is equal to 80 liters, which is 0.08 meters cubed. That's what 80 liters is, divided by the mass. So this is the total volume of the tank, and if you divide by the mass, so the therefore the specific volume, so then the specific volume of the tank, the mass is 4 kilograms, so this is divided by 4 kilograms, and therefore I'm going to go to the left here because I'm out of space. So 0.08 divided by 4 kilograms is equal to 0.02 meters cubed per kilogram. So that's our V here. So our little v. So little v is 0.02 minus v sub f, which was a table lookup, 0.0007435, and then divided by v sub fg is basically v sub g minus v sub f. So it's 0.1235 minus, again, v sub g, 0.0007435. Sorry about this. I'm starting to touch a little button here on this pen that's driving me nuts. Okay, so this is now equal to 0.157. So this is equal to 15.7% is the quality, and that means that 15.7% of the mass of this tank is vapor. And now that we found X, so we'll go ahead and can check that off our list. And now we need to find the total volume of the, I'm sorry. Can we find the total? Yeah, the total volume. Well, let's just go ahead and let's leave it at that. And maybe we can just find, if we were to find, so we've already talked about how to find the total volume. All we need to know is find the volume of the vapor, and you can go ahead and just look at the example to find how to do that. To find enthalpy at that point, we need basically enthalpy of the liquid. This is at 160 kilopascal minus X times H sub Fg. And this is so H sub Fg, H sub Fg is basically Hg minus Hf, and these are table values that you can go ahead and subtract, but it's also given in the table. So if you look, this is all at 160 kilopascal. If you look up in the table 160 kilopascal, you're going to find an entry labeled H sub Fg, but that's simply put against, it's the enthalpy of the vapor minus enthalpy of the liquid. You can calculate it, but oftentimes it's already given there. So we have everything here. This is a table lookup. This is 15.7%. So you put it down as 0.157. And this is also a table lookup. So then we can find the enthalpy. All right, so I think we're going to stop there. And this concludes our discussion, chapter 3, about saturated liquid vapor mixtures.